In this video, I'm going to briefly introduce you to the idea of concepts and constrained templates. So this is in chapter 21. So far, we have seen many templates and the function templates and class templates mostly. There's also alias templates, right? So where you can use the using keyword to define various different alias types. That's also templated. And so those are the main templates you have seen so far. And we have specified the template parameters just with, either a type name or non-type parameter. There's different kinds of parameters you can use in the templates. And then we just simply use them. And we haven't really said much about, okay, how do you prevent people from passing, various different types into your template that is actually not even compatible with your template code? Basically we'll just throw up and something goes horribly wrong. So the templates we have seen so far are unconstrained. That's basically saying there's not a whole lot mechanism that's preventing the consumer of your template to passing any kind of arguments. Now, if they do pass the ones that are not compatible with the intent of the template, the templates, and then they basically will get all kinds of errors. The requirements as far as those arguments that can be passed to templates typically are implicit. Perhaps they are documented in a comment. So, or just somehow is unspoken. Then you somehow the consumer needs to look into your template to see what kind of arguments they need to pass in. And if you're being a good programmer, you may use a reasonable name for the template parameters that will give an indication what they might be. And yeah, that's the best we can do so far. And the problem with that is when the user passes, an argument that is, it seems reasonable, but they get all kinds of errors anyway. And those errors typically very difficult to understand. In fact, let's take a look at an example, actually. It's probably, so let's look at the the example of 2101. And 2101, let's open up, take a look at this. So let's say I have an empty class here, and then I will make a variable of a vector v, which takes reference to int, and now we'll make some objects of my class, right? Then we determine which one is the maximum using the standard max function template. And then we may just make a set of objects that is an object of my class. And then we just do some operations about it. Okay, so so you wonder, well, what could be wrong? And I just saw the output here. We tried to compile. It did not compile. And then the error throughout was some strange things that's kind of into the standard library. There's a, X memory talks about, pointer, and the pointer to reference is illegal. Now, if you follow down, then you see, well, there's this allocator and of reference to ints that cannot be compiled. And then there's more details following about the allocator. And then there's, a bunch of, okay, then there's something about a vector, right? It goes into the standard library where, well, it says something, kind of really strange statement. Okay, so it's difficult to really understand. Now, if you just look through this, right, it's very hard to, okay, figure out what was wrong. Now, excuse me. Now, what is wrong here is that the vector cannot take reference types. As a container, it cannot take reference types. This is it's just not allowed based on the definition of this vector class. This is a standard vector class. Now, if we say, let's try to fix it, let's see what kind of stuff we're going to get. All right, failed again. Now, this time is something different. Now it talks about a utility, which is a standard library. In the standard library, it talks about the binary less than operator. And it's saying that kind of another type does not define this operator. And that type is called a my class. Well, this is actually a little better than before. If you look down here, it's actually invoking the standard max function template, right? And then here it's complaining about that less than operator not available. Okay, it kind of makes sense, right? The max template, the function template must be trying to compare the objects one and the other to see which one is bigger, right? Makes sense. But then of course, this my class is empty. It doesn't implement anything. It doesn't overload any kind of operator such as less than. And that's what's required by this max. So to give you a little taste what kind of error you might get. Now, if let's say we comment this out. See comments. All right. Let's comment this out and then let's see what kind of error we're going to get again. Okay, we see different errors. So this time it talks about in the algorithm library, the binary minus. Well, this is a kind of it looks like it's a subtraction, the subtraction operator. And it says that list, well, something about that list. I see all these names are weird internal names. There's in the implementation of the libraries. It says does not define this operator. So something about that list does not define an operator of, is the list iterator not defining the operator for calculating the difference between two iterators. Now this kind of depends on some understanding, but the thing is, if you look at the output of all these things and types, they are compiler specific, by the way, and they are internal template implementation code. And if you look at the, kind of at the bottom, and it talks about trying to sort. So it looks like this statement is complaining about, well, kind of just educated guess. And then we have some random iterators and the iterator tray, a difference type. Okay, there's an expected for arguments to be provided. Okay, so this is the kind of statement that throws an exception, but the exception is not very easy to understand at all. Okay, so this just kind of gives you a taste of, the difficulty of using templates so far with the, unconstrained templates, in the sense that the parameters are not declared with any kind of constraints. And then when you use things wrong, and it's difficult to debug. Okay, so that's kind of the point. So instead, the improvement here is to use constrained templates. Now, what are constraints? Constraints means really saying, okay, this parameter, it has to follow certain constraints. If saying that it has to be this kind of type, it can do this kind of stuff. It has to say overload certain operators, right? Certain things need to be available for that to be, to make sense in this particular template, the way we're using it. So the constraints, we're going to look at how to define them in a moment. But the constraints, what that will provide us is that first is a clear documentation on what template arguments are allowed. And the other thing also, the constraint is in the form of code. So the compiler is going to actually tell you what's wrong if you're using that in a wrong way. And usually what that means is that if you have multiple constraints, they all have to be satisfied. If they're not satisfied, the templates will not be instantiated. The compiler will just simply just stop it. It says, well, can instantiate the template with this argument to the template, because so and so constraints are not satisfied. And that really just means there's a much better error messages if we are passing improper arguments to the templates. The way to define constraints, of course, in the C++20 standard is using concepts. Now, was there a way to do that before concepts? Yes, there was a way. And it has to do with the techniques associated with the template metaprogramming. And it gets really complicated, by the way. It's not very intuitive. The book mentioned a technique called CIS-17A, and you can look that up. There's a good explanation on Wikipedia. you can see if you understand. Now, those techniques were there because there was a strong need for constraining the templates, and there wasn't a language feature to do so until C++20. So now we have this thing called concepts. So a concept is a named set of requirements. Essentially, the constraints we're talking about so far. Now, formally with the concept, there are basically requirements. These are the things that are required. And there are different types of requirements. First one is syntactic. So the syntactic requirements means this kind of expression, if, let's say you have a type, I want to say this expression, say this type, I want to use it in a addition, +1. I want to make sure that is valid because this is important in the implementation of a template. It's one of the things that I need to assume that type parameter supports it, right? So it can be any kind of expression. So this saying, syntactically, this expression should compile. This is really what the syntactic means, okay? It compiles. And then there's a semantic next higher level of a requirement. It's called semantic. Semantic, that means the meaning of it, right? The meaning of the expression. The expression should evaluate properly. it does not only compile, but also runs properly, calculates result correctly. Okay, so this is another requirement. Now, problem is, it's kind of difficult to enforce that semantic requirements. Now, it's not impossible. For example, when you write a code, you normally with the proper software engineering, you write tests. The tests are there essentially could be to enforce the correctness of your program. Potentially that could be, sort of a mechanism to define semantic requirements. It's not in the standard. It's kind of, I would say it's kind of something that's difficult. I'm not saying it's not possible in the future. But as of now, you cannot express semantic requirements in concepts. And what we have to fall back to is basically documentation, right? And then the highest level, well, not necessarily highest level, I would say even more difficult to enforce in code is the complexity requirements. Now, complexity we're talking about is the complexity of the algorithm. So there's, say, if this requirement is about a particular operation or a function call, right? And we're saying the way this function call is implemented through a certain algorithm, that algorithm has to satisfy some kind of a time or space complexity constraints. So if you know about this, like for example, the big O notation, right? It needs to be evaluated in constant time or in linear time, right? This kind of constraints for both running time and space, that can be also expressed. Typically what you see in the standard, of course, is basically just documented. Saying, okay, for example, for certain type of operations, the standard will say, well, this takes constant time, big O over 1. The big O notation, you can look that up if you haven't studied. Now, this is beyond the scope of this course. Just want to mention this for completeness here. Now, how do you define a concept? So a general format for defining a concept is it got this line of template parameters, right? It's just like how you define any kind of a templates. And so that part is the same. You have seen many times, function templates, class templates, or alias templates. And then we use a keyword concept to indicate this name that follows is a concept. And keep in mind, the concepts are not objects you can use at a runtime to, it doesn't serve that purpose. This is used for compile time checking. And it's typically used to, help, again, so basically saying for, let's say you define a template and you want to constrain the template parameters. You want a compiler give you a proper error messages when the usage of the template is wrong because a certain type of arguments doesn't satisfy certain type of constraints. And that's really the purpose of a concept. So then, the way to define that is in terms of a list of concepts, constraints, excuse me. So here are some basic examples. Let's say we can define now, by the way, this constraints is basically a Boolean expression that needs to evaluate to a Boolean, exactly Boolean type, not something that's convertible to Boolean. Okay, and actually it needs to be a compile time constant, and means that it has to be able to, it's evaluated at a compile time. So remember this whole concept is everything is in the compile time. So let's say we are defining an integer concept in terms of other concepts. There's two other concepts. There's a word defined called a signed integer or an unsigned integer. And then so an integer is either signed or unsigned. And those concepts also take template parameters, right? take an argument here. And by the way, with the concept, it needs to take at least one argument, because what's the point of having concept if it's not constraining any kind of type? This typically, that's why at least should have a one type of parameter in the template header here. And then, well, the logical expression here, you can use this logical, or you can also logical and, right? So it's showing you another example where you have a random access iterator. Now, iterator, this is explained in the standard template library video. And so this is essentially the way to loop through the collection of elements in a container. And the random access kind of, an example of a random access is the array, the index of an array. That is a random access iterator in a sense. Well, iterator, you need to wrap that in an object, but essentially that gives that feature of you're able to access randomly based on some kind of a location indicator. So the iterator has a hierarchy, and a random access iterator is the most flexible kind. Is basically, it is a bidirectional iterator and also some other things as well. And these other things we cannot, okay, so how do you define other concepts here? We'll see, okay, example is we're making concepts out of other concepts. You're composing a new concept based on existing concepts. Yeah, so this is showing you this is you can do, but how do you define an actual concept with a specific constraints? So the way to do that is to use the requires expressions. And requires is a keyword here, and so use the requires, and then with in the braces you can put basically a sequence of requirements here. And this requires also can take a parameter list, just like a function, by the way. Similar to a function, there's like the parameter list and they have a body. So the parameter list is optional, basically, that's the first form. So here's an example. This requires well, actually, the iter is the template parameter to this concept that we're trying to define. And so let's say we're trying to constrain an iterator. So the concept of iterator. And specifically, this iterator needs to follow certain kind of constraints here and or requirements. And so the first requirement here was saying this expression I plus one, which is an iterator object, plus one, this should compile. Well, essentially saying this iterator should support this, the addition operator that needs to be overloaded. This is really what this means, right? So this is a so-called a simple requirement, okay? Similarly, you can say, I less than j. That's, talking about the less than operator is overloaded. That can be used to operate, between two iterator objects. And then this one here is a compound requirement. And in the sense that, well, this is what it's called, but it just means it's a little bit more complicated here. Well, there's two things new. First, it says this expression should not throw an exception, right? The no except. So you remember the no except functions. So here we're using the same keyword here to indicate if I have this expression, and basically your implementation, this the plus operator here should not throw an exception. That's basically what we're trying to constrain. If it does throw, like if it's not declared as no except, okay, that means it violates this requirement. The compiler is going to tell you. And then with this arrow here and on the other side, this is saying the return type of this expression should be the same as the iter type. So remember, I is the iterator, and then plus one, this should also return another iterator. So, okay. The same as, by the way, as you see, is in the standard namespace. So it's actually a standard concept. So this is constraining the return type of that expression. Well, it needs to evaluate to this type. This saying is the same as this type. So if it doesn't do that, like the overloading, the addition operator does not return that type, then that would be an error. Okay, so this is another requirement. And another example is there's this convertible to standard concept. So by the way, the standard defines many concepts. You should use the standards as much as you can. And so this convertible to saying, okay, so this I less than j was not saying it needs to return a Boolean value, but whatever that value is returned needs to be convertible to bool. So it's more relaxed. So which is fine. So that's if you say that's your requirement. Okay, so it just shows you another example. This is another compounded requirement. So there are more requires expression, by the way. So here we're actually looking at this requires clause inside the requires expression. Sorry, requires expression inside this concept definition here. So, oh, by the way, this range is range. This is another standard concept, is defined in the ranges library. It's saying that this type needs to be a range. We're trying to define the concept of string. So inside this requires expression, and we have two different types. So first is this type name that you're familiar with, but in the context of here, it's called a type requirement. We're saying this type S should have a member type, value type as a member of S, and this value type needs to be a type. Okay, not a value, but it's actually a type. Well, basically means it could be a nested class, it could be a enumeration, it could be a let's say a type alias, right? So it needs to be a type. This is saying, okay, this needs to exist and also is a type. So this is another, it's called a type requirement. And now, and then the next one it shows basically saying you can nest the requires expression here. So when you have another requires inside of requires, well, typically you do nesting because it needs to take a parameter set, that's passed into this parameter list here. And then the example here doesn't take it, but just, if it doesn't take it, you can take this out, right? You can actually take this outside of this requires, so you don't have to nest it, and you can use another and, logical and so that will be fine as well. So here, this is essentially saying, well, first, this value type is a type, and then we're going to use that type here to say this type is actually a character type. Okay. So this is, which is another constraint. Well, assuming that we defined it, this is another concept here. So the value type needs to be a character. So with no string, basically is a range of characters. Then so let's take a look at another example. So recall this array class we had previously. Let's say, suppose we want to turn this into a function object class, and it overloads this function call operator. Okay, and then here the example saying, well, this function call operator takes a index parameter. Essentially, it does the same thing as the subscript operator. Okay, so it delegates to that subscript operator that's overloaded on this class. And so we simply just want to turn this into a function call, because we talk about the first class functions. How do you constrain a type to be a function object? So here's an example, right? This is simplified. And so here it shows you another type of parameter in the template is called a parameter pack. So that means 0 or more types here, and then they are used together as a pack. And so you use this dot, dot, dot. So like this is, say we have another, this way, say with arguments. Well, I'm going to use this. Typically, this is for variadic arguments. So let's say the concept of function objects, we need to require given an object of t and a list of arguments, an argument parameter pack. So we're using this args type. By the way, this is parameter pack. This is the type. And then we're actually declaring an object here, which is a list of arguments. And when they are expanded with the dot, 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 the args object with the dot, dot, dot followed, that is basically saying expanding that arguments if it's 0 or more in that parentheses. Okay, so we're actually invoking a list of arguments on a object of t. And we're saying, okay, this is like a function call, right? So we're saying if it has a function call operator overloaded, then this is a function object. Well, there can be other constraints, requirements you can put on, but this is just saying we're talking about the essential stuff here. All right. And then the static assert is a declaration. Again, this is a special utility you can use, and this is not a macro, by the way. It's a declaration, and it will be used by the compiler to check what's passed in. It's this expression compile time, whether that is true or false. So we can use this concept expression. So this is a concept, and then we are specializing, passing in the arguments to the concept function object. So we're passing in a type. This is we're trying to verify this array, right? This class is what we are interested in. We're trying to constrain it. And well, and basically we pass that, we say, well, we say this array actually supports a function call operator that takes an argument of a size type, right? Just like this, okay? If this takes different list of arguments, then you can, use this doesn't need to change, and then just use those types here to specify. And this will be, they will allow you to verify if this array follows the concept, well, models. If it passes this, means they said was saying this array models this concept. And so this is how you check if it actually models that concept at compile time. So this has no cost at a runtime, by the way. This is all done at a compile time, okay? And will not be executed at a runtime. And how do you use this concept? There's so here, this is actually what we're already talking about using it in the sense that to verify a class, models a concept or not. But we eventually want to use this to constrain templates, right? So let's introduce this standard concept, totally ordered, and we're going to use this in a second. The totally ordered standard concept specifies that comparison operators and all these standard operators, they are on this type T, they yield results consistent with a strict total order, which is a mathematical concept on this type T. And really that strict total order means that, you have A less than B if A is less than equal to B and A is not equal to B. So that's the mathematical definition there. And so anyway, if you're interested, so this is a totally ordered concept. And we're going to use this in let's say we got a function template here. So in the past, we may use, type name or class, their equivalents. Okay, so this is for saying we have a type parameter. Now this type parameter here now is not, preceded by a type name keyword or class keyword. Instead, we're using a concept here. So of course, it's very intuitive to understand. That means this type, we're saying type T is totally ordered. That's a constraint on this parameter we'll pass into this template. And of course, it makes sense if the type T is totally ordered, and then we can actually operate, we can use this operator here, like, greater than, less than. This may be more than what we needed in this implementation, but the idea is that we want to use coherent set of concept definitions that will, instead of kind of just looking at your current implementation and so do the bare minimum, that is not recommended way of doing it. you have to put this in a larger perspective. And what is the things you're trying to compare with? Which one is larger? And then the specific constraint really that suits that scenario is totally ordered types. Um, and other types that will, if as long as you implement this operator, could work. But and again, so the idea is you should just have a minimal set of, is in fact most of them are already in the standard, and use them, and there are sort of coherent set of concepts that you can use throughout your program, and that also allows you to evolve your implementation. Say, well, today I'm using the greater than, tomorrow I'm using the less than. Okay, if you say that type T implements greater than, today it works, tomorrow it won't work anymore because now we change the implementation to less than operator because it doesn't have that implemented. that is not very good. It doesn't make sense, right? So instead, you just ask upfront about what the notion of this type is supposed to be, and then you try to use a concept like that, not to make a concept totally based on your current implementation, because that implementation is going to evolve. Okay. So there's an alternative way of constraining templates. So here we see we're using the concept name here for constraining the type in these angle brackets. But you can also use this requires clause. Now, this requires clause is equivalent to the ones you can use in the concept definition that we just talked about, the requires expression there. Now, what this allows you to do, though, is essentially saying you can define a ad hoc concept like this. So typically, if it's a short, you're using other concepts that would probably okay. And sometimes it could be more readable if you have a couple of requirements that you want to constrain your type with. So you're combining a couple of them, and then, but unless it's a reusable piece of a concept, and then you probably want to just define a concept for that. But otherwise, this allows you to write the constraints this way, okay? Now, here's another example. Now, why that requires clause? The requires clause here, we're saying we can use this in the template, the template declaration there to say, well, this is constrained the type on the template. But then if you're using that class templates here, you can further constrain your member functions with that requires clause. So you have constraints for the template types, but then you also have constraints for the member functions using that same requires clauses. So for example, this is a copy constructor. And then we're saying the concept for this member function, it needs to, in order for this to work, the element type T for this array container needs to be copyable because we're going to copy element inside this implementation here. So that's a requirement. Makes sense, right? Similarly, the move constructors, and we say this element type T needs to be movable. Now, these are standard concepts, so you can just reuse, right? And this would be a good idea to do, by the way. Now, here we're just talking about a couple of standard functions. And then, so this is just an example to show how you might use this so that if I pass a type, for an array, you're passing something that's not copyable, and you're actually trying to use the copy constructor. And by the way, when you're using instantiating the template of an array, if you're not using a particular function, even if that type violates a particular, the method function, so the member function specific requirement, if that's violated, but you're not using that function for that type, that is fine, by the way. So it only kicks in when you're trying to use it. and the compiler will check if this satisfies the requirements, whether there's a violation or not. All right. So it gives a lot of flexibility how exactly how you're going to use it. So this is just a decent example how you might use the concepts in your class definition, class templates. Now, I show this table here is that in the standard, there's actually a lot of, before we had a concept, there's a lot of named requirements. And they were requirements. There's like, okay, so for this, these are the, actually, by the way, these are the 6 special member functions, remember, right? These are the special 6 special members of a class. And there was this actually named requirement. Essentially, they are documented, say this is the requirement, this is how it's supposed to behave. And it wasn't really sort of enforced in terms of a code. So we're able to do that now with the concepts. And so there's actually standard concepts already made that can enforce those named requirements in code. So just kind of show you that, there's actually a lot more standard concepts to show you what might be available for those. These are the basic class related constraints or requirements. So in summary, all the template parameters should be constrained. And well, that's probably a good habit to do. It's basically most of the templates that are designed with constraints in mind. A template is not going to work on any kind of type, right? It's typically you have some kind of constraint saying this type needs to follow certain requirements so for this template to make sense. And a concept is a named set of requirements defined with concept expressions. A concept expression means in terms of other concepts, then you can combine them to make a new concept, right? And also you can use the requires expressions, and then we'll know you can do different kinds of requires expressions. You have a simple expression, right? And then you have compound requirement, you have type requirement, you also have what is the other one? There's 4 types of requirements if you look at the requires. So you have a compound and you have nested. Yes, so you can also nest that. You can those are the 4 things you can use in the requires expressions. A well-defined concept always corresponds to proper semantic notion. That's what I was talking about in that function template example of a larger function template that is saying you don't want to just make a concept or constrain your template types based on the present implementation. It should be based on the semantic notion of the type that this operation is intended on, and try to use that notion, which is some kind of coherent concept, instead of some kind of ad hoc implementation specific requirements. And I did not provide an example here. Just want to mention the placeholder types such as auto, pointer to auto, and those variants, right? Reference to const auto. These are the placeholder types that allow the compiler to deduce the actual type. This can be constrained as well to say, okay, I want you to deduce it, but then the deduce type should also be constrained. Say I have a particular concept called my concept, and then you say my concept auto. Use that in your function parameters or in the in the declaration of a variable. That's saying now I'm not going to just accept any kind of a type here, and I want to constrain that deduce the type. So that's another usage there. Now let's switch to looking at more code here, these examples. So let's look at the second example here. Now this is, so we'll talk about the iterators there. And by the way, this would be the simplest concept. This does nothing. It's like, like a void type kind of thing. This saying this concept equal to true, of course, this means any kind of type will satisfy this concept. Okay, it's true, right? There's It doesn't do anything. And then we'll talk about, you can define a concept in terms of other concepts, right? You have, say, this needs to be your iter class, needs to be a bidirectional iterator, and with a requires expression here, and there's a bunch of things we're testing. So you see those are compound requirements here, and we have seen those examples before. And then here is another concept called no except destructible. Well, destructible, by the way, that is a standard concept that's already there. It's called destructible. Now here saying we're defining our own, well, which is probably not as good as a standard. So you always prefer the standard one. They are battle tested. And because it's kind of difficult to get a concept right. So here shows an example, right? So you have, so you're passing a reference to this type T, and this value invoking this, the destructor, right? That's the name of the destructor starts with a tilde. And then we use this no except. So remember the compound requirement. You can constrain the exception throwing property as well as the the type, the return type of the expression. All right, so there's a couple more things here, but then I just want to scroll down to, so we're seeing the example of a static assert. Now, static assert is a declaration. It's not really a macro. It's not an operator. This is some, again, is a facility you can use to check whether a type models a concept. So this is saying, want to see if this string class has a destructor that's no except. Well, we know all the destructors are by default no except. So that's not a problem. Of course, they're all going to satisfy. This is simply just, for illustration purposes here. Okay, so just want to show you that. Now, here's another example, the number 3, this array class. And right, so here we're saying the array elements concept. Okay, this array element concept is saying this the array type, with this specialized with a T, and that's a type name, right? And then we're saying this array, this particular element type, we're saying unique pointers, and this is a valid type or not. Okay, so but by the way, this is a little different from the example in the book, because this is how MSVC does not support a requires clause here directly in the static assert. So that's why I had to make a very simple concept here to do it this way. Okay, then here's the function object example, and then you can run this. Of course, the so what's happening here is that remember that function call, this function operator overloaded, that's the equivalent to the subscript operator, and then we're getting the element at index 10, which is this value 1, 2, 3. Okay, and then we're dereferencing, well, that unique pointer. Remember, this is the element type is a unique pointer, and this returns a reference to a unique pointer, and this essentially dereferencing it to get the value out of it, which is obviously 1, 2, 3. And take a look at another example here. And this shows you the requires clause to constrain the template parameters. And this is actually used, you see, this is combined with the concept. You use the concept to constrain for the type, but it also adds a required clause. You can use both, of course. And actually, this example shows you how the compiler is going to pick which template to take, because you see you have two templates. They all take a single template parameter, a type parameter, and then which is constrained differently. And this says this type is a random access iterator, and this is saying this is an input output iterator. This is a more restrictive, more specific. This essentially saying is input output iterator, and there's equality operator defined for iterator type. And then this is random access. So with a random access iterator, of course, by definition, the distance between the two iterators essentially just use this subtraction operator. So that is supported on a random access iterator. That's basically by its definition of that concept. Now, if it's just an input output iterator, it doesn't support random access, then you have to loop through the elements in that range or sequence. And then you advance the iterator like that, and then you're basically then trying to count how many elements in between as the difference. So this is less efficient, of course, and this is obviously is constant time. Here is you're having a loop here, and so this is showing you the standard list container that is not a random access iterator. Remember, this is a linked list, and the vector is backed by an array that gives you random access. So the iterator on that is random access. So this will show you essentially we'll have a different, message printed out. This will say this is a linear traversal. This is a constant time in the case where you have a random access iterator. So now if you run this, so it will basically say that list is linear. We're using the linear traversal here. This distance between the particular templates picked is the first one, because the iterator by calling the C begin on the list object, that gives you iterator from a list, and that list iterator satisfies the input output iterator and also the equality comparable concept. But it will not satisfy the random access iterator. And that's why that first the linear traversal template is picked. And when you use the vector iterator satisfies this random access iterator concept here. So that's why this is picked. Now, here's the thing. Of course, the random access iterator also satisfies this, but this is a more specific, more restrictive, so to speak. And this more specific constraint, this version of the template will be picked for this second function call here on a vector iterator. Now, same thing with this pointer. Now, remember this array name, we said this is like a const pointer. And pointer allows you to do random access as well. So it's equivalent to, it has this property of random access. So this also is going to pick the second template here that takes the random access iterator as a constraint. Okay, so that's pretty much about it for the concepts. Thank you.